Hey everyone, welcome to Equivalence Relations with me. Today we're going to talk about when things are the same, like up to a certain point. In order to do that, we're going to need to talk about three different types of relations though first. First kind of relation that we're going to talk about is the reflexive relation. That means that we always have like X paired with itself in the relation. This is not the identity relation because you can have more than that in there. So it's like the identity relation and more. A quick note. The identity relation is going to be a subset of R. So for example, if we were to have a relation on just people in general, we could say that one relation would be person X knows person Y. Hopefully you know yourself. So we're going to say that X, comma X is in R, but also we have, like if X is me and Y is my friend Kat, we would also have XY in the relation. So it's not just the identity relation. We still have other stuff in there. Now, something that wouldn't be reflexive would be like talking about kids. So we've got person X is going to be Landon. And person Y is going to be me. We've got X and Y will be in the relation. However, Landon is not his own kid, despite how much he might want that. And so X, comma X is not going to be in the relation. Okay, next type of relation, symmetric relations. That means if we have a pair XY, then Y is also going to be related to X. For example, if we have person X and person Y, and they have a class together, then it works the other way around because otherwise you're not in class together, something creepy's going on. So if we have, we'll say you, we'll say person sitting next to you. This is in a theoretical classroom that we obviously do not have right now. We have X and Y would be in R, but also Y and X would be in R. It doesn't matter which order you say it in. However, back to the kid again. We have X is Landon. We have Y is me. Landon is my kid. However, again, despite Landon's protests, I am not his kid, even if he does make me dinner sometimes. And then one more type of relation, transitive. We should all be very familiar with transitive, I think at this point. If X is related to Y and Y is related to Z, then we have X is related to Z. For example, we're going to talk about hair color. If we've got X and Y have the same hair color, so we'll say X is Kat and Y is me. And I'm going to say, get a third person in here, so Jazzy. Jazzy has the same hair color as me too. So, there we go. We're both brunettes with this ombre-ish thing going on. Same with me and Jazzy. But that also means that Kat and Jazzy have the same hair color. Okay, so we had both of these, but we also had this one. That would be a transitive relation. Something that would not be transitive would be X knowing someone. So we've got X would be, what would that be? I'll say you. And Y is going to be me. and Z is going to be cat. I know you. I am your teacher. I know Kat. She is my best friend. I would honestly be very surprised if you knew Kat. So X and Y, we know each other. Y and Z, we know each other. However, you do not know Kat. Unless maybe you're in computer science. Maybe. But in general, you get the point. It's not a given. So this is not a transitive relation. So putting all three of those things together gets us a really special kind of a relation, and it's called an equivalence relation. And that's when it's reflexive, symmetric, and transitive all at the same time. So we've got a couple of relations to go through, and we're going to decide which ones of these are going to be equivalence relations. So first we talked about reflexive, then symmetric, and then transitive. Okay, so first off, we've got R. We've got X knows Y. We already said that one was reflexive. Now, if X knows Y, hopefully Y knows X as well. We're going to say know as in like the deep personal relation, deep personal relation, rather than, oh, I know this person on YouTube and they have no idea about my existence. Not that kind of knowing. Transitive, we already discussed, not transitive. And then we've got X is Y's kid. We already discussed that one is symmetric, right? That one's not symmetric. I am not Landon's kid. So we discussed that it was not symmetric. We also discussed that it was not reflexive. And turns out it's not transitive either. So if Landon had a kid, that would be my grandkid, not my kid. And then C, we have the one where there's class together. So you definitely have class with yourself. I hope you bring yourself to class every day. And then we already discussed that it was indeed symmetric. And then it's not transitive. So let's say you have Math 381 with somebody, and then you have chemistry with somebody else. Your Math 381 study buddy and your chemistry study buddy are not necessarily going to be the same person. Or they might not know each other. That's what I meant. They might not have a class together. Okay, and then the last one, we've got same hair color. I have the same hair color as myself. And if I have the same hair as, or same hair color as Kat, Kat definitely has the same hair color as me. And then we already said that, yes, it is transitive. So this one is an equivalence relation. And then these ones were not. So now that we have equivalence relation, now we get to, we're going to discuss something mathy instead of just talking about people. So here's a new thing for us to talk about in math. We have not discussed like congruent modulo stuff. So we say that X is going to be congruent to Y modulo M, which is a mouthful and I can't even say it, if M divides X minus Y. And I don't know, I just like looking at this better. It just makes me feel a little bit happy on the inside. I don't know, it's easier for me to digest. If that is the case, we write X equals Y mod M. Let's look at a couple of examples, get used to it for a moment. We say that 2 is equal to 12 mod 10 because 12 minus 2, that would be 10. So 10 divides 12 minus 2. And then we can also do 5 is equal to 12 mod 7. Because if we do 12 minus 5, that's going to be 7 right there. So 7 divides that. Doesn't have to be smaller. So these two examples, we had 5 is smaller than 12, 2 is smaller than 12. Could be bigger. Let's do an example for that. If we do 26 minus 12, that's 14. 7 does indeed divide that. And then last example, you can have 0 is equal to something mod m, because 12 minus 0 would just be 12, and 2 divides 12. Alrighty, so since we have that now, let's do something going back to relations. I want to prove that if x and y come from z cross z, then that the modulus thing that I just defined is going to be an equivalence relation, which means we need this relation to satisfy reflexive, symmetric, and transitive. Let's get going. First thing we're going to prove. We're going to prove that it is indeed reflexive. How do we do that? Well, we start, remember, reflexive means this is going to be an R. So we just start with an arbitrary x, and we need to prove that the pair of them are going to be in there. So we've got let x be an element of z. I don't like it. There we go. So what we know is that 0 is divisible by anything. Remember, the goal is to get like x is going to equal x mod m. That way we can say that x comma x is an element of R. This means that we need x minus x to be divisible by m. 0 is divisible by anything. So there we go. That's going to be our missing link. So we know m divides 0. Why do we know that? Because by definition of divides, we can do 0 equals m times 0, where 0 is a perfectly valid integer. So that means we're going to use that thing that I just erased where x minus x is 0. So then m divides x minus x, because x minus x is equal to 0. And then by definition of mod, we have x equals x mod m. Therefore, x is indeed in R. So that's reflexive. Next one we're going to do is symmetrics. So symmetrics a little bit different because our starting point is different. Now for these ones, it's like mostly about figuring out how to start the proof. What is your first step? Remember, symmetric means that x comma y implies y comma x is going to be in R. So that means we have to start with this and get this is true. Let's get rid of that and see if we can do it. So let x comma y be an element of R. Then we can say we're going to apply what it means to be in R, which is the modulo stuff. Y equals, or x equals y mod m. So then m divides x minus y. And then what do we do with this? Well, we have a definition for divide, so let's go ahead and apply that just to see where it takes us. X minus y equals mk, where k is going to be an integer. And then, so that's what we want to do. So we're hoping for y comma x is going to be in R. That's where we want it to end, which means running it backwards, we're hoping for y equals x mod m, which means we want to have m divides y minus x. So do you notice how I keep doing this work backwards thing to figure out where my proofs are supposed to meet? It's totally legal, totally advised. But if someone were to read my proof, they would never know because it is organized so that it doesn't look like I worked backwards. Okay. So in order to have it divides this, that means I need to be able to write y minus x equals basically some k bar. So to make that meet up here in the middle, that would be like saying, let's multiply both sides by -1, right? So that I can switch the order that y and x are in. Same thing as multiplying both sides by -1. And so that's going to be m times -k, and then -k is going to be our integer. So then if -k is an integer, that means we have m divides y minus x by definition of divides, which means we have the definition of modulo, which means we have y comma x is going to be in R. And then I'm going to run through and be a good mathematician and write why all these lines are true. So by definition of congruence, and then this one was by definition of divides, and then nope, I'm off by 1. Boop. Boop. Oh. Okay. This is also by definition of divides. There we go. I have justified. Next one. So we did reflexive, we did symmetric. Now we've got to do transitive. Last one. And I knew it wasn't going to fit, so we've got a new slide for this. So remember, transitive is we've got x and y, and we have y and z, and we want to get xz is going to be in there. So that means we have to start with 2 elements, xy and yz are going to be in R. And we're going to work up to this guy. So then what can we do? We can apply what it means to be in R. So we've got x is equal to y mod m, and y is equal to z mod m. And then from here, now we can do the definition of what it means to be like congruent. So then m divides x mod y, or x minus y. It's an m word. And m divides y minus z. Once again, we're going to just chase this definition. This was definition of congruence. We know what divides mean, so that's the next definition we're going to invoke. So we've got x minus y is going to equal mk, and y minus z is equal to mj, where k and j are going to be in here. Oh. Definition of divides. Okay. And then what do we want now? This is where I go to the end of the proof and I'm like, I don't know, what do I want? So I want x comma, nope, z to be in R. So then in order to get there, that means I need x to be equal to z mod m. And then to get there, that means I need like x minus z to be equal to m, we'll say L. Okay, so I need x minus z to equal m times an integer. That's the new end goal. I can do that. So we've got this, we've got this. And what I want to do is I want to add these two equations together because I can see that here on the left side, those y's are going to cancel out. And that is good news for me. So then x minus z is going to be equal to x minus y plus y minus z. And then I have something for x minus y. I know that's going to be mk. I know that was mj. So then this is going to be m times k plus j, where k plus j is an integer. There. Let's do it this way. Perfect. And then that turns into the definition of mods, which turns into it is in R. So we have transitive. And then what was the goal of this again? The goal was to prove that R was an equivalence relation. We have symmetry, we have reflexivity, and we have transitivity. Now we're done. Therefore, R is an equivalence relation. All done. Okay, so there you go. That's how you would prove a math thing that is an equivalence relation. But we're going to take this a little bit more. We're going to talk, remember the big goal was we wanted to talk about things that are the same up to a point. So like if I gave you like some qualifications, I would want you to be able to tell me like all the things that are the same in that regard. And that's what's called an equivalence class. So we say that we have an equivalence class of some element x. So I say, hey, I want something to be the same as x. And then I tell you I want it to be the same as x in this particular way, R. And then we denote it. X has the equivalence class of this guy, which is all the y's that are going to be related to that x. So they're all the same up to that relation. For example, going off of what we just had, let's say I wanted to know x mod, or x is going to equal y mod 2, and I want to know the equivalence class for 1. So that's the same thing as saying if x is 1, we've got y mod 2. And so if I subtract the y over, I want to be able to divide it by 2. So what are all the y's that are going to let me divide this number over here, 1 minus y, by 2? We can hazard a really good guess. If it's odd, then 1 minus y will be even, divisible by 2. Now we have to prove it though. We can't stop. So we want, let's set a goal. So So we want all the y's such that 1, y is in R. All right. So what do we start with? We want to discover, I already said, I kind of gave away the punchline, but we want to discover what kind of y's this is going to be. So we do 1, y is going to be an element in R. So that means that 1 is going to equal y mod 2, which means 2 is going to divide 1 minus y. So by definition of congruence. So then by definition of divides, we can write this as 1 minus y is going to be equal to 2k for some k that is an integer. There we go. And then we're trying to figure out what y's are going to work. So then now we're going to do a solve for y. So 2k. Yes. And I'm going to rearrange that a little bit so it matches our definition of odd. Negative k is indeed an integer. So then y is odd. So what I have proven so far, give myself a little, is that what have I proven? Said that if it's going to be in the equivalence class, then it's going to have to be odd. So now the question is, do all odd numbers work? So now I'm asking, do all odd numbers belong in the equivalence class? I said that if it's going to be there, it has to be at least odd. But does that mean that's enough? Is that a good enough qualification? It's odd and we're in? Well, now we're going to start at the bottom. We're going to say if y is odd, we're going to prove that it's in the equivalence class. So let's think about this. If y is odd, then we're just going to apply the definition of odd. So we can just turn around and go up that step. If it's odd, then we can definitely rearrange it to look like this guy right here. I'm going to make these green so that it matches my question. There we go. And then once we have that it looks like this, we can definitely say that matches the definition of divides. And then that matches the definition of congruence. And so then if it fits this format, that means it's in R. So there we go. We've got forward direction. What did we do? In the forward direction, just to summarize, if y is in the equivalence class 1 determined by R, then y is odd. So no evens allowed. But then in the reverse direction, which was, we'll say in green, so if y is odd, then y is going to end up in our equivalence class. So all the odds. First we did, it has to at least be odd, and then doing it backwards gives us, if it's odd, then we're good. So therefore, we know, so now we know exactly all of everything that's going to be in our equivalence class. So we can say 1 determined by R is all y's in the integers such that y is odd. Okay. So there you go. That's how we determine if things are the same, like up to a particular point, at least in math terms. That's all I have for right now. So I'll talk to you later.